Somewhere tonight, someone steps outside after dinner, coat half buttoned, keys already in hand, and glances up at the sky the way people have glanced up at the sky since long before there were doors to step out of. Orion is there, low and unhurried, exactly where it always is at this hour in this season. The 3 stars of the belt, the faint smudge of the sword, and up in the corner marking the hunter's shoulder, a star burning the soft orange red of a coal that hasn't quite gone out. Nothing about it looks urgent. The person doesn't linger. They get in the car, or they don't, and the night goes on being an ordinary night. That's the last night anyone will describe it that way. Because somewhere on the other side of the planet, where it's already morning, a very different kind of glance is happening. An astronomer on the early shift, coffee cooling beside a keyboard, pulls up an automated brightness alert she assumes is a glitch, the way you assume most things at 6 in the morning are glitches. She checks it anyway. Then she checks it again. Then she stops reaching for the coffee. By the time the rest of the world wakes up, the story has already outrun anyone's ability to explain it calmly. Phones are lighting up in observatories on 4 continents. A subject line with too many exclamation marks is making its way through a mailing list that has not seen this many replies in 30 years. Someone, somewhere, is trying to explain to a very confused radio producer why a star doing something unusual is actually the biggest news of the decade, and not managing to make it sound as enormous as it is. Ordinary people are noticing too, in the ordinary ways people notice things. A jogger on an early loop stops mid-stride because the sky looks wrong without her being able to say how. A man walking his dog glances up out of habit and glances up again out of disbelief. Nobody is panicking yet, because panic requires knowing what to panic about, and right now all anyone has is a faint, prickling sense that the sky has rearranged itself slightly overnight without asking. Here's what's happening in the plainest possible terms before we let it get complicated. Overnight, without warning, one of the brightest and most familiar stars in Earth's sky has changed. Not dimmed, not flickered. Changed in a way that every serious instrument pointed at it agrees is not a mistake, not an atmospheric trick, not a satellite passing in front of a lens. Something has happened to the star marking Orion's shoulder, the one sailors used to steer by, the one that's been sitting quietly in humanity's peripheral vision for the entire span of recorded history. And every possible explanation keeps arriving at the same word, spoken a little disbelievingly by people who trained for years not to say it lightly. Supernova. Its name, for those who haven't met it properly yet, is Betelgeuse. Tonight, we're going to spend a couple of hours with it. Where it came from, why this was always going to happen eventually, what's actually occurring up there right now, and what it means that a star can undergo the most violent event in the universe and have nobody notice for centuries. Get yourself comfortable, because this is a longer story than it first appears, and it has a very strange relationship with time. If you'd like something gentler after this, a river finding its way across a continent, or a body quietly keeping itself alive without asking your permission, the sleepy geographer and the sleepy biologist are waiting for you whenever you're ready for them. For now, settle in, let your eyes close if they haven't already, and let's find out what's happened to the shoulder of the hunter. Because somewhere tonight, that same star is still hanging there in that same patch of sky. Whatever has happened to it up close happened a long time ago. What we're about to live through together is only just arriving. There's a particular kind of silence that falls over a room full of astronomers when nobody wants to be the one to say the obvious thing out loud. It fell that morning at an observatory in Chile, where a graduate student named Nobody Remembers Who had pulled up the same data everyone else was pulling up, stared at it for a long moment, and finally said what everyone was thinking, in the flattest voice she could manage. It already happened. Not, it's happening. Not, it's about to happen. It already happened. Somewhere hundreds of years ago, in a place none of them would ever be able to visit even if they wanted to, a star's core collapsed in on itself in less time than it takes to read this sentence, and the only reason anyone on Earth was finding out about it this particular Tuesday morning was that light, however fast it travels, still has to travel. This is the part of the story that tends to make people go quiet the first time they really sit with it. So let's sit with it properly, because the rest of tonight only makes sense once this part has settled in. Betelgeuse sits around 640 light-years from Earth. The number moves around slightly depending on which measurement you trust, because getting an exact distance to a star this size and this restless has turned out to be surprisingly difficult. But 640 is close enough to build a life around. A light year, in case the phrase has gone a little fuzzy since school, isn't a unit of time at all, whatever it sounds like. It's a unit of distance, the distance light travels in a single year, which works out to something like 6 trillion miles. 640 of those stacked end to end is the gap between here and there. Light is fast. It's the fastest thing there is, as far as anyone has ever managed to measure, and nothing in the universe is allowed to beat it. But fast isn't the same as instant, and over a distance like that, even the fastest thing there is starts to feel less like a messenger, and more like a very, very slow letter. Picture it as an actual letter, if it helps. Imagine that the moment Betelgeuse's core gave way, someone up there, purely hypothetically, there's no one up there, but bear with the image, sat down and wrote Earth a note. Dear Earth, something enormous has just happened to me. You'll want to sit down for this. They sealed it, sent it off at the only speed the universe allows for sending things, and then had to wait, and wait. The note travelled through the dark for 640 years, passing nothing, stopping for no one, while entire empires rose and fell in the time it took to cross the gap. It was already on its way when the first stones of a cathedral were laid in a city that didn't yet have the name it has now. It was still travelling when that cathedral was finished, and still travelling long after everyone who laid those first stones had been forgotten. It was travelling during wars nobody currently alive studied in school, and it was travelling during wars everybody currently alive did study in school, and it was travelling this morning while a graduate student in Chile reached for a coffee she never got to drink. The letter arrived. That's all that happened last night, an old letter finally delivered. It's worth sitting for just a moment longer with how long 640 years actually is, because the number slides past easily in a sentence and loses most of its weight in the process. 640 years ago, nobody on this planet had ever heard a word printed on a press, because the printing press hadn't been invented yet. Entire languages spoken back then have since gone quiet, replaced by languages their own speakers would find unrecognizable. The maps people trusted back then were mostly guesses, filled in with sea monsters wherever the guessing ran out. Every person who was alive when that core collapsed, every single one without exception, has been dead for centuries, and through all of it, undisturbed by any of the wars or plagues or inventions or quiet Tuesday mornings that filled those 640 years down here, that first burst of light kept crossing the dark at the same relentless, patient, uncomplaining speed, headed for a planet that hadn't yet worked out it was going to need to know this. Which raises the question, gently for now because it deserves more room than one chapter can give it, of when, exactly, something can be said to have happened. Is the explosion an event that occurred 640 years ago in a place too far away for anyone to have witnessed it? Or is it an event that's occurring right now, tonight? Because tonight is the first moment anyone in this solar system has had any evidence that it happened at all. Both answers feel true. Neither answer feels complete. It's the kind of question that seems simple until you actually try to answer it out loud, at which point it turns out to have no bottom, and we'll come back to it, properly, all the way down, before the night is through. For now, here's the more immediately useful way to think about it. Astronomy is the strangest kind of history there is, because every single object in the night sky is a kind of time capsule, and some of the capsules are older than others. Look at the moon and you're seeing it as it was a little over a second ago, practically live by cosmic standards. Look at the sun, and you're seeing 8 minutes into the past, which is why, if the sun ever did something catastrophic, we'd have 8 minutes of blissful ignorance before finding out. Look at the nearest other star system, and you're peering 4 years back. And look at Betelgeuse, glowing patiently in Orion's shoulder, and you're looking not at a star, but at a photograph, a 640-year-old photograph taken by starlight itself, developed slowly across the intervening centuries, and delivered to your exact location at the exact moment you happen to be standing there to receive it. Every stargazer who has ever looked up at Betelgeuse, the sailors who steered by it, the shepherds who named it, the countless ordinary people glancing up after dinner without giving it a second thought, has been looking at old news without knowing it. Beautiful old news, certainly, but old. There's something almost comic about it, if you let yourself see it that way, in the dry, deadpan sense that the universe seems to specialize in. Humanity built its entire understanding of the night sky on light that was, in many cases, already ancient by the time it reached us. And for centuries, nobody thought to ask whether any of the stars up there were still exactly as advertised. It's a bit like admiring a postcard someone sent you from a city that, unbeknownst to you, doesn't exist anymore. The postcard is real. The photograph on the front is real. It simply isn't necessarily still true, which is precisely the position every observatory on the planet found itself in that morning. What they were looking at wasn't a star behaving unusually. It was the record of a star having already finished behaving in every way it was ever going to behave, its story already over, its ending already written, centuries before anyone on Earth had the faintest idea anything was wrong. The astronomers weren't watching an event. They were reading its obituary, and the obituary had simply taken an extraordinarily long time to arrive in the post. By mid-morning, every major observatory with a view of that patch of sky had confirmed the same reading, independently, in the particular tone scientists use when they've checked something so many times that doubt has stopped being useful. Telegrams. Nobody actually sends telegrams anymore, but the phrase persists because nothing else quite captures the urgency. Went out to every corner of the professional astronomy world. Meetings that had been scheduled about entirely different things were quietly repurposed. Somewhere, a very tired conference organizer was rewriting a keynote speech at short notice, and somewhere else a professor was standing in front of a lecture hall trying to explain to 200 undergraduates why she'd abandoned her prepared slides, waving vaguely at a laptop, while the room slowly stopped checking their phones and started actually listening. It's a strange thing to watch a room full of trained skeptics stop being skeptical all at once. Astronomers spend their careers being suspicious of exactly this kind of reading. A sudden dramatic signal is far more often a faulty sensor than a genuine event, and the field has learned the hard way many times over to check and check again before believing anything spectacular. But by noon that day, the check-in had simply run out of places left to go. Every instrument agreed. Every independent team, working without knowledge of what the others were finding, arrived at the same answer. The skepticism didn't collapse so much as it quietly retired, having done its job thoroughly and found nothing left to object to. And somewhere in Chile, the graduate student who'd said it out loud first sat with her cold coffee and watched the data confirm itself over and over, thinking, as it turned out correctly, that she was witnessing the beginning of the most talked about night in the history of her field, and that none of it, strictly speaking, was actually beginning at all. It had already ended, 640 years ago, in the dark, without an audience. Tonight, finally, Earth gets to watch. There's an observatory in Arizona where, on a clear night, a retired schoolteacher named Nobody Important Enough to Name climbs a short flight of external stairs every evening around 9, sits down at a telescope she bought herself 20 years ago, and points it at exactly the same patch of sky she's pointed it at for 2 decades. She isn't looking for anything new. That's rather the point. She's looking for something old, something reliable, something that will be exactly where she left it the night before. And for 20 years, it always has been. Tonight, for the first time, it wasn't, which is as good a moment as any to actually sit down and get properly introduced to the star responsible for ruining her routine. Its name is Betelgeuse, and if you've ever had a passing conversation about it, there's a fair chance you've been mispronouncing it with total confidence, which is honestly the correct way to do it. Even astronomers argue about whether it's Betelgeuse or Betelgeuse, and the honest answer is that nobody alive can ask the 10th century Arabic astronomers who first named it, so everyone's just doing their best. The name itself comes from a phrase meaning something like the hand of the giant, or the armpit of Orion, depending on which manuscript and which translator you trust, which is a wonderfully undignified way to refer to one of the most spectacular objects in the night sky. The universe rarely consults us on matters of poetry. What it marks, if you've never had it pointed out, is the shoulder of Orion, or the armpit, depending on which naming tradition you're following, one of the 2 bright points at the top of the hunter's most recognizable outline, up and to the left of the 3 neat stars that make the belt. It burns with a distinctly warm orange-red glow that stands out even to the naked eye against the cooler white-blue of most of its neighbours, and that colour alone tells you something important before we've said a single word of physics. This is not a young star. Blue-white stars are burning hot and fast. The soft ember red of Betelgeuse is the colour of a star further along in its life, cooler at the surface, and, though nobody watching it glow gently overhead would necessarily guess this, considerably more dangerous underneath than its calm colour lets on. Here's where the numbers start doing something numbers aren't really built to do, which is stop making intuitive sense entirely. Betelgeuse is what astronomers call a red supergiant, and supergiant is not one of astronomy's more restrained words. If you could somehow relocate Betelgeuse to the centre of our solar system, in place of the Sun, its outer surface would swallow Mercury, Venus, Earth, Mars, and the asteroid belt, and would keep expanding outward past that, engulfing Jupiter, before finally running out of star somewhere in the neighbourhood of Saturn's orbit. Our entire solar system, the one that currently comfortably contains 8 planets and a great deal of empty space, besides, would fit inside this single star with room to spare. It is, by volume, something on the order of hundreds of millions of times larger than the Sun, a number so far outside ordinary experience that saying it out loud doesn't really help anyone picture it, so it's probably more useful to just picture the Saturn thing again and let that sit. And yet, this is the part that trips people up every time. Betelgeuse isn't especially heavy for its size. Mass and volume in a star this puffed up and swollen have almost nothing to do with each other. Despite being large enough to swallow half the solar system, Betelgeuse only weighs somewhere in the range of 16 to 20 times what the Sun weighs, which sounds like a lot until you compare it to the volume and realise the material it's made of is spread so thin, so diffusely across such an enormous swollen bulk, that if you could somehow bottle its outer layers, the result would be closer to a very good laboratory vacuum than to anything you'd recognise as solid. It's less a star in its outer reaches and more a star-shaped suggestion, an idea of a surface, held together loosely by gravity that's had to stretch itself thin to cover so much ground. That looseness shows. Point a serious telescope at Betelgeuse and you don't get the tidy symmetrical disk you might expect from a star. You get something closer to a slow-motion boil, vast, roiling patches on the surface, some of them individually large enough to swallow the orbit of Mars, rising and sinking as titanic convection cells drag hot material up from somewhere deep inside and cooler material back down. It isn't smooth, it isn't calm, it's closer to the surface of a pot of soup left on a very, very slow simmer for an inconveniently long time, if the pot was several hundred times wider than the Sun and the soup were made of plasma. In fact, Betelgeuse holds a small but genuine piece of scientific history for exactly this reason. In the mid-1990s, it became the first star ever, other than the Sun, to have its actual surface directly imaged rather than merely inferred, a grainy, mottled photograph taken by the Hubble Space Telescope that finally let astronomers see, rather than calculate, that this was not a smooth ball of light, but something closer to a slow-boiling, ever-shifting thing with genuine weather. It also doesn't hold still in brightness, which is where our school teacher's broken routine comes back into the story. Betelgeuse is what's called a variable star, meaning its brightness swells and fades over time, on multiple overlapping rhythms at once. A slower wobble stretched across roughly 5 or 6 years, layered on top of a faster one closer to 400 days, the two rhythms interfering with each other in a way that makes its overall brightness genuinely difficult to predict from one season to the next. On its brightest nights, it ranks among the 10 or so most brilliant stars visible from Earth. On its dimmer stretches, it slips quietly down the rankings, noticeably fainter to anyone paying close attention before climbing back. It's less a single fixed point of light than a very, very slow, very patient pulse, and we'll spend real time later tonight on the strangest and most talked about of these dimmings, the one a few years back that had half the astronomical world briefly convinced the end might be imminent. For now, it's enough to know this a star that breathes visibly on a time scale long enough that a single human lifetime barely covers a few dozen cycles of it. None of which explains quite why people have cared about this particular point of light for as long as they have. Part of it is simple visibility. Betelgeuse is bright enough and distinctive enough in colour that it's been impossible to overlook in every culture that ever bothered looking up. Part of it is position, sitting where it does, on the shoulder of one of the most universally recognised patterns in the sky. It's essentially impossible to describe Orion at all without eventually landing on this star, whether you learn to find it as the red one from a grandparent, a scoutmaster, or more recently, an app pointed skyward on a phone. And part of it, honestly, is that oddly ember-warm colour itself, sitting there in a sky mostly populated by cooler white and blue points of light, looking for all the world like a single coal that never quite went out, glowing on regardless of what century happens to be passing beneath it. Which brings us at last back to that shoulder, or armpit if you're following the older translation, and to something happening on the other side of the world from that Arizona observatory in a backyard where nobody yet knows what's about to dominate every news cycle for the next several days. A father is standing with his daughter after dinner, her first time properly outside after dark, without immediately being hurried indoors, and he's doing what parents have apparently been doing for as long as there have been parents and children and clear nights. He's pointing up, tracing the shape of the hunter with one finger, working his way across the belt and then up to the shoulder. That one's called Betelgeuse, he tells her, not entirely sure he's pronouncing it right, not remotely aware that he is introducing his daughter, on this particular night of all nights, to a star that the rest of the world is about to spend a great deal of time discussing. She squints, follows his finger, and finds it, a small, warm, orange point, holding steady above the horizon, utterly unremarkable to her, exactly the way it's looked to every child who's ever had it pointed out before her. She has no way of knowing that the star she's looking at has, in some very real sense, already stopped existing in the form she's seeing it in. Nobody standing in a backyard ever does. That's rather the whole story tonight, and it's time we went looking for the reason why. There's a specific kind of person every town seems to produce at least one of. The one who works 18-hour days, burns through 3 jobs before 30, throws parties that people talk about for years, and is, by general consensus, going to either accomplish something extraordinary or collapse spectacularly by 40, possibly both. And then there's the other kind, the one who takes the same steady job at 22 and is still doing it, quietly, competently, 45 years later, having never once made the local news for anything at all. Nobody ever tells stories about that second person at parties. But if you wanted your affairs handled reliably for the next half-century, you know exactly which one you'd hire. The sun, whatever else you want to say about it, is the second kind of person. It has been fusing hydrogen into helium in its core at a steady, unglamorous, essentially unchanging rate for 4.5 billion years, and it is on track to keep doing exactly that for roughly 5 billion more before it even begins to think about slowing down. It has never had what you'd call an eventful day. It gets up, it shines, it goes to bed, metaphorically, and repeats on a timescale so vast and so uneventful that boring starts to sound less like an insult, and more like the highest possible compliment you could pay a star you happen to be orbiting. Betelgeuse is the first kind of person, and to understand why a star can burn 20 times heavier than the sun and still be dying while the sun is barely getting started, you have to get comfortable with one of the more counterintuitive facts in all of astrophysics. Having more fuel does not mean lasting longer. If anything, in stars, it means the opposite, and the reason why is worth sitting with, because it's the whole engine driving tonight's story. A star holds itself up against its own gravity by burning fuel in its core, nuclear fusion, hydrogen crushed together under unimaginable pressure until it becomes helium, releasing energy outward that pushes back against the star's own weight, trying to crush it inward. It's a fight, permanently, between a fire trying to expand and a mass of material trying to collapse, and for most of a star's life, the fight is roughly a draw. The trouble starts with mass, A heavier star has more weight bearing down on its core, which means more pressure, which means a hotter, more frantic core, which means the fuel gets consumed at a drastically faster rate, not proportionally faster, but dramatically, absurdly faster. Double a star's mass and you don't double its fuel burning rate. You might multiply it by 10 or more. It's less like a bigger car with a bigger tank going the same distance, and more like a bigger car with a bigger tank that also, for reasons of its own, has decided to floor the accelerator the entire way and never let off it. More fuel, yes, vastly, disproportionately more speed. The tank empties faster than it filled. This is why a star with only 20 times the Sun's mass can burn through its available hydrogen, not in 10 billion years, but in something closer to 8 or 10 million, a difference so large it barely feels like the same unit of measurement is doing honest work in both sentences. 10 million years sounds enormous by the standards of a single human life, and it is. By the standards of a star, it's a season. Betelgeuse formed, by most estimates, somewhere around 10 million years ago, which means that at the moment its core finally gave way, it had already lived out the overwhelming majority of whatever lifespan it was ever going to get. Not from bad luck, not from some external calamity, but purely because it was born heavy, and heavy stars have never, in the entire history of the universe, been offered the option of taking things slowly. And once the hydrogen runs low, the reckless spending doesn't stop. It accelerates. A star like Betelgeuse doesn't quietly run out of fuel and fade to black the way you might expect. Instead, its core starts collapsing inward under gravity's renewed advantage, which raises the temperature further, which is hot enough to ignite a new fuel, the helium ash left over from the previous stage, and buys the star a bit more time, at a bit more expense. Helium fuses into carbon and oxygen. Then, when that runs low, the same trick again. Collapse, heat, ignite the next available fuel. Carbon into neon and magnesium. Then oxygen into silicon and sulfur. Each stage shorter than the one before it, dramatically, almost comically shorter. Where hydrogen burning lasted millions of years, the carbon stage might last centuries. The neon stage, roughly a year. The oxygen stage, mere months. And silicon, the final stage, the one that produces iron in the core, burns for something on the order of a single day. It's worth pausing on that shape for a moment, because it's genuinely one of the stranger rhythms in nature. A star's death isn't a gradual dimming. It's a countdown that keeps halving its own remaining time, stage after stage, faster and faster, like a book whose chapters keep getting shorter until the final one is a single sentence, and the one after that doesn't exist at all. Millions of years, then centuries, then a year, then months, then a single day. By the time you reach silicon burning, whatever process built this star up over 10 million patient years has compressed itself down into something that would fit, start to finish, inside a long weekend. Imagine, for a moment, trying to live a human life on the same compressed schedule. Childhood, adolescence, the slow accumulation of a career, stretched out across decades, exactly as it should be. Then, somewhere in late middle age, everything starts happening faster. A decade's worth of change in a year's worth in a season. By the very end, entire chapters of what used to take a lifetime are being lived out in an afternoon, and the final one, the one that used to represent years of a person's life, is over before dinner. Nobody would call that a graceful decline. It's closer to a life playing itself backward through a zoom lens, each stage smaller and faster than the one before, right up until there's no more room left to compress into. And then, Having raced itself all the way down to Iron, the star hits a wall that no amount of gravity or pressure or desperate ingenuity can get around. Every fusion stage up to this point has released energy. That's the entire reason the process works, the entire reason it can hold a star up against its own weight for as long as it does. But Iron is different. Iron is, in the specific technical sense that matters here, the most tightly bound nucleus there is. Fusing it doesn't release energy, it consumes it. A star that builds up an iron core hasn't found a new fuel. It's found the bottom of the barrel, a substance that offers no further resistance to gravity at all. There's nothing left to burn that will push back. This is where the countdown ends completely. For millions of years, gravity has been pulling inward and fusion has been pushing outward, a contest so evenly matched that from the outside, a star looks essentially motionless for most of its life. The moment an iron core forms at the centre of a star like Betelgeuse, that contest is simply over. Gravity has no opponent left, and gravity, unopposed, does not negotiate, does not slow down to consider the matter, does not politely wait for anyone to be ready. It wins immediately and completely, and the core that took 10 million years to build collapses in on itself in a fraction of a second. A span of time so short that moments is generous, and we'll spend real time with exactly how short, and exactly what that collapse unleashes before tonight is done. For now, here's the shape of it, and it's worth carrying forward as its own kind of answer to a question from earlier tonight. Massive stars aren't unlucky. They aren't victims of some cosmic accident that smaller, steadier stars simply avoid through good fortune. They're paying, on a schedule fixed the moment they were born, for exactly the qualities that make them so bright, so visible, so impossible to ignore in the first place. The same mass that makes Betelgeuse brilliant enough to mark a hunter's shoulder for every stargazer in recorded history is the very same mass forcing it through 10 million years of fuel in the time it takes smaller stars to barely get started, the same mass guaranteeing, from the moment the star first lit up in whatever nebula gave birth to it, that this ending, in some form, was never a possibility. It was always, from the very beginning, simply a matter of when. In late 2019, an amateur astronomer in Chile, a genuine hobbyist, the kind who points a modest telescope at the same handful of favourite stars every week purely for the pleasure of it, noticed something was off about Betelgeuse and did what hobbyists have done for centuries. He mentioned it to people who'd listen. Betelgeuse looked dim. Not subtly dim either. Over the course of a few months, it had faded to something like a third of its usual brightness, dropping low enough in the rankings that people who'd spent their whole lives using it to navigate the winter sky were squinting upward and wondering if they'd gotten the wrong star. Professional observatories confirmed it within weeks. By December, half the astronomical world was watching the same star with the same unspoken question, sitting behind every measurement. Is this it? Is this what the beginning of the end actually looks like? For a few months, nobody could rule it out, and that uncertainty, it turns out, is worth taking seriously as its own kind of story, because it's a rare, honest look at what it actually feels like to stand at the edge of not knowing something enormous. Talk shows booked astronomers who spent entire segments carefully explaining the difference between "we don't know" and "it's definitely about to happen," a distinction that made for frustrating television, but happened to be the only honest thing anyone could say. Telescopes that were supposed to be pointed at entirely different patches of sky that season quietly found reasons to swing toward Orion instead, and in observatories the world over, a particular kind of scientist, the sort who has spent an entire career being professionally unimpressed by dramatic-looking data, found themselves checking the same numbers 3 and 4 times, not because they doubted the instruments, but because some part of them wanted, quite badly, for this to be the ordinary explanation rather than the extraordinary one. Here's what we do know happens in a star's final stretch, whether or not it happens to announce itself the way Betelgeuse's dimming appeared to. As a red supergiant approaches the end of its fuel-burning life, it doesn't do so quietly. The same giant convection cells we've already met, those slow-boiling patches on the surface, individually large enough to swallow the orbit of Mars, become more violent and more erratic as the core beneath them destabilizes, dragging material up from deep inside the star and flinging some of it outward entirely. Red supergiants are famous for shedding mass this way throughout the later parts of their lives, breathing out great slow exhalations of gas that drift off into space and cool, over time, into fine dust. It's not dramatic to watch most of the time, a star quietly losing weight, a little at a time, the stellar equivalent of shedding a coat it no longer needs. But every so often, the shedding is dramatic. A large enough eruption of material, cooling fast enough, can form a genuine cloud, a curtain of fresh dust, drifting directly between the star and any telescope, unlucky or lucky enough, depending on your perspective, to be pointed at it from Earth. Which turned out to be almost exactly what happened in 2019. Detailed follow-up observations, visible light, ultraviolet, careful modelling of exactly which patches of the star had dimmed and by how much, eventually pieced together a clear picture. A colossal blob of plasma had been ejected from Betelgeuse's surface, rising up through the star's outer atmosphere, cooling as it went and condensing into a genuine cloud of dust, large enough to blot out something like a quarter of the star's visible face from our vantage point. It wasn't the star growing fainter from the inside out. It was a curtain, drawn temporarily across part of the stage, and once enough time had passed for the dust to disperse and drift away, Betelgeuse brightened back up, more or less exactly as it had been before anyone got worried. So, not a warning sign, strictly speaking. A dramatic, genuinely unprecedented event in its own right. Nobody had ever watched a star do quite that in quite that much detail before. But not, in itself, evidence that the end was imminent, which might sound like the story resolves there, tidily, with a sensible explanation and a slightly embarrassed astronomical community putting its telescopes down and getting back to normal life. Except it doesn't, quite, because the great dimming was only the most dramatic chapter in a much longer, much stranger pattern of behaviour that Betelgeuse had been exhibiting for as long as anyone had been carefully measuring it, a slower, 6-yearish wobble in brightness, layered over its more familiar shorter cycle, that nobody had ever managed to explain convincingly. The dust cloud accounted for one extraordinary dip. It didn't account for why the star had been quietly, rhythmically misbehaving on a longer timescale for decades before that. That part of the puzzle sat unresolved for years, the way genuinely difficult puzzles tend to, occasionally mentioned in papers, occasionally the subject of a hopeful new model that fits some of the data and not the rest, without anyone quite landing on an answer that satisfied everybody. And then, more recently, it did resolve, not through some dramatic new event, but through astronomers finally managing to see something that had apparently been there all along, hiding in plain sight in the glare of a much brighter neighbour. A faint companion star, orbiting Betelgeuse far closer in than anyone had confidently confirmed before, finally directly detected, using painstaking work, with some of the most capable telescopes and cameras available, specifically designed to cut through the overwhelming brightness of the giant star sitting right beside it. It was given a name of its own, Siwarha, and with it came, at last, a satisfying explanation for the slower wobble that had puzzled everyone for so long. As this companion star swings through its orbit, it passes through Betelgeuse's vast, loosely held outer atmosphere, stirring up a wake of disturbed gas behind it as it goes, not unlike a boat cutting a visible trail through still water, and that stirred-up wake, drifting and dispersing, is what had been rhythmically dimming and brightening the giant star's appearance from Earth's vantage point for decades. Which means the honest answer to, could anyone have recognized the warning signs, turns out to be quietly, satisfyingly humbling. Astronomers had been watching real, measurable rhythmic changes in the star's behavior for years, and reasonably wondering whether they meant something dire. What those changes actually meant was that Betelgeuse had a dance partner nobody had properly seen yet, cutting elegant, gas-stirring laps through its atmosphere on a schedule of its own. It's the sort of resolution that doesn't happen often enough in science to stop being satisfying every single time it does. Not a mystery solved by discovering the star was dying after all, but a mystery solved by discovering the whole question had been slightly wrong from the start. Nobody needed to ask, is this a warning sign of collapse? They needed to ask, is there possibly something else out here we haven't spotted? And it took the better part of a century to get around to asking it properly. None of which means there's no genuine early warning available at all. There is, but it comes from somewhere far stranger than surface brightness. In the final day of a massive star's life, as the core races through its last few fusion stages, it starts producing a flood of ghostly particles called neutrinos, the same particles in far smaller numbers that stream constantly and harmlessly through every one of us, through the Earth itself, without a single one ever really interacting with anything on the way through. In a dying star's final hours, that flood becomes immense, and unlike light, which gets trapped and scattered and delayed by the star's own dense material on its way out, neutrinos slip through almost entirely unimpeded, escaping the collapsing core hours before any visible sign reaches the surface at all. Detectors built to catch exactly this kind of event exist right now, quietly listening. And if Betelgeuse's core does eventually reach that final, unstoppable moment, those detectors may well register a flood of neutrinos hours before anyone sees a single change in the sky above. Hours, not months, not years. After 10 million years of borrowed time, the only genuine advance warning nature offers is measured in hours, arriving through particles nobody can see, felt by instruments built for exactly this and nothing else. Whatever final months a star like Betelgeuse spends in its last true stretch, the shedding, the dimming, the companion cutting its long quiet laps through the gas, none of it, it turns out, is the warning. The warning, when it finally comes right at the very end, and by the time anyone reads it, there's no longer any months left to speak of at all. The phone starts ringing at 3:47 in the morning, which is never a good sign for anyone, but is a particularly bad sign for an astrophysicist who happens to have their office number quietly plugged into an international alert network most people have never heard of. She's awake before the second ring, the way you learn to be after enough years on this particular list, and she has the message read before she's fully sitting up. A facility on the other side of the planet has just registered a flood of neutrinos pouring out of the general direction of Orion, thousands of times the normal background rate, arriving within a handful of seconds of each other, across 3 independent detectors on 3 separate continents. That kind of coincidence doesn't happen by accident. It happens for exactly one reason, and every person on that alert list knows what it is before they've even had coffee. Something's core just collapsed. We left Betelgeuse a little while ago at the worst possible moment for it, a star that had spent 10 million years slowly building up an iron core, only to discover that iron offers absolutely nothing back to a fight against gravity. Fusion had, for the entire life of the star, been the only thing standing between star and catastrophe, and iron marked the exact instant that support finally, permanently gave out. So let's go back to that moment and stay there, because everything else tonight has been leading up to it, and it deserves to be described properly. The core of Betelgeuse, at the point of collapse, is roughly the size of the Earth and contains something like 1.5 times the mass of the Sun, crushed into that comparatively tiny volume. The moment fusion stops pushing back, that entire mass begins falling inward, all at once under its own weight. Not gently, not gradually, but at a meaningful fraction of the speed of light, the whole core collapsing from something Earth-sized down to something roughly the width of a city in well under a second. There's nothing in ordinary human experience remotely equivalent to this. It isn't a building collapsing, or a dam breaking, or an avalanche. Those all take seconds or minutes because they are fighting friction and air and structural resistance the whole way down. This is a star-sized mass, falling through essentially nothing at all, restrained by nothing at all, for a fraction of a second, until it slams into itself so hard that the collapse simply cannot continue. The core, having fallen as far as physics will allow, suddenly refuses to compress any further, and the whole collapsing mass rebounds off itself in an instant, sending a shock wave tearing back outward through material that, half a second earlier, had been falling the opposite direction entirely. And in that same instant, actually slightly before the visible drama even gets started, an almost incomprehensible flood of neutrinos escapes outward from the newly formed, unimaginably dense core. This is where the numbers stop being merely large and start being genuinely difficult to hold in your head at all. In the first few seconds after collapse, the core releases something on the order of 100 times more energy, total, than the Sun will produce across its entire 10 billion year lifetime. And the overwhelming majority of that energy, something like 99% of it, leaves in the form of neutrinos, those nearly weightless, nearly interaction-free particles that pass through planets the way sunlight passes through a clean window. For a few seconds, this dying star outshines every other star in the visible universe combined, in a form of light that no eye, no telescope, nothing built to see with photons can detect at all. The most powerful event any of us will ever hear about happens first in near total silence, in a kind of light nobody can see, noticed only by a small global network of very patient, very specialized detectors built for exactly this and nothing else. The same network that just woke our astrophysicist up at a deeply unreasonable hour. This is the answer, finally, to something we've been circling since early tonight. The neutrino burst leaves the core and crosses the star's own outer layers essentially unimpeded, slipping through hundreds of millions of miles of the star's own material in seconds, because neutrinos barely notice matter is there at all. Light has no such privilege. The shock wave, the actual physical explosion tearing outward through the star's bulk, has to fight its way through all that material the hard way, colliding with it, heating it, pushing it, and that takes time, hours in fact, before it finally reaches the star's visible surface, and the first true optical sign of the explosion becomes possible for anyone, anywhere, to see. which means that for several hours Betelgeuse's core will have already finished its transformation, its neutrinos already having raced outward and off into the universe, while the outside of the star still looks, to any onlooker, however impossibly distant, completely unchanged. The explosion, in other words, does not merely happen once at one time in one place. It happens first invisibly in particles, and only afterward, hours later, in light. And that's before we even get to the 640 years the light itself will need to cross the gap to Earth. Ask, when did Betelgeuse explode? And you're not choosing between two answers anymore. You're choosing between at least three, stacked one inside another like a very strange kind of nesting doll, each one true, none of them complete without the others. Once that shock wave does finally break through the surface, though, the show that follows earns every bit of the word spectacular. Over the following hours, the star's brightness climbs with a speed nothing else in nature manages, brightening by a factor of tens of thousands within a single day, transforming what had been one moderately bright star among thousands into something that can, at its absolute peak, briefly rival the combined light of every other star in its home galaxy put together. Over the following days and weeks, the light continues climbing before eventually beginning its long, slow decline, the freshly exposed material cooling and thinning and fading, the whole visible spectacle stretched out across months in a way the invisible foundational part of the process, the actual core collapse, never was. There's something worth sitting with in that mismatch of timescales because it says something true about how enormous events actually unfold, as opposed to how we tend to picture them. We imagine explosions as instantaneous, a flash, a bang over in a heartbeat, and the true instant of collapse genuinely is that fast, faster than fast, a star's inner architecture giving way in less time than it takes to blink. But the consequences of that instant, the part everyone actually gets to witness, take hours to reach the surface and months to fully play out across the sky, a slow-motion unfolding stretched across an almost unbearably long span, given how quickly the whole thing actually started. The violence is instant. The story it tells afterward takes its time. It's a bit like grief, if you'll allow the comparison. Not a perfect one, but a useful one. The event itself, the moment something changes forever, can be over in an instant. A phone call, a diagnosis, a door closing. But the part that everyone on the outside actually witnesses, the part that has to travel outward through everything in its path before anyone else can see it, unfolds much more slowly, in stages, over hours and days and months, long after the single instant that actually caused it has already come and gone. Betelgeuse's core knew, in less time than it takes to finish this sentence, the rest of the universe would need a great deal longer to find out. Back on Earth, tonight in our story, the night this news finally arrives after its 640-year journey, our astrophysicist has, by now, made it into the office, coffee finally acquired, watching the same confirmation come in from detector after detector, each one independently agreeing with the last. She isn't thinking particularly about how far away the actual event is in time, about the centuries that separate what she's looking at from whatever's happening at that location right now. This instant, if right now even means anything sensible across a gap that size, she's thinking mostly the way most people in her position would be thinking at 4 a.m. with cooling coffee and a phone that will not stop buzzing, that she is looking for the first time in her career, in anyone's career, at genuine proof that somewhere, a very long time ago, something extraordinary and irreversible happened to a star that generations of ordinary people had trusted to simply always be there. It was. And now, whether anyone up there ever gets to know it or not, it no longer is. By that evening, a video has been watched several million times, in which a man standing in what appears to be his garage explains, with the calm, unshakable confidence of someone who has clearly never once been wrong about anything, that the exploding star currently dominating every news channel on the planet is going to blind anyone who looks directly at it, strip the ozone layer within the week, and quite possibly end complex life on Earth by the weekend. He is not an astronomer. He is, according to the caption, just someone who does his own research. And by the time actual astronomers get around to responding to him, his video has already been shared roughly 900 times more than any of their careful, measured explanations ever will be. This, it turns out, is simply how the news of a supernova travels through a modern information ecosystem. The calm, accurate version limps along in second place, forever, while the apocalyptic version gets a head start it never gives back. So let's do the calm, accurate version anyway, because it happens to be far more interesting than the garage broadcast gives it credit for, and none of the genuinely spectacular parts require inventing an extinction event to justify the excitement. We'll start with the most basic question. How bright is this actually going to get? Here, history is generous enough to offer real precedent. Humanity has watched supernovae before, just never one quite this close. In the year 1006, a star exploded roughly 7,000 light-years away, and by every surviving written account from observers in China, Japan, Egypt and Europe, all independently describing the same object, it became bright enough to read by at night and was clearly visible in broad daylight for weeks, brighter than anything in the sky besides the sun and moon. Less than 50 years later, in 1054, another exploding star, this one the origin of what we now call the Crab Nebula, did something similar, visible in daylight for the better part of a month, bright enough that observers on the other side of the planet, with no way of communicating with each other, wrote down almost identical descriptions of a strange new star that simply hadn't been there the night before. Betelgeuse sits vastly closer than either of those, roughly 10 times nearer than the 1006 event, close enough that the comparison stops being merely impressive and starts being almost difficult to responsibly estimate, because nothing this close has gone supernova in the entire span of recorded human history. The honest scientific answer is a range rather than a single number, but the low end of serious estimates already puts it bright enough to be clearly, unmistakably visible in full daylight for weeks, and the higher end of those estimates has it briefly rivaling the brightness of a crescent moon, a single point of light, casting actual shadows at night, bright enough to read by without any other light source at all. Somewhere in a park, on the night this happens, more than one person is going to notice they can suddenly see their own shadow stretched out on the grass with no idea where the extra light is coming from. Look up and understand. Which brings us to the question the garage broadcast got so spectacularly wrong. Is any of this actually dangerous? Here the physics is refreshingly reassuring and worth explaining properly rather than just dismissing. The genuine hazards a supernova can pose to a nearby planet, a burst of high-energy radiation capable of damaging a planet's protective atmosphere, thinning its ozone layer, and exposing surface life to harmful levels of ultraviolet light, are real, documented, physically well-understood things. They're also things that only matter within a fairly specific range, generally estimated at somewhere under 50 or so light-years. Betelgeuse, at roughly 640 light-years away, sits more than 12 times beyond even the outer edge of that danger zone. Whatever radiation eventually reaches Earth from this event will have spent centuries spreading out across an ever-expanding sphere of space, thinning by the time it arrives to a level so far below anything biologically meaningful that instruments will register it as a scientific curiosity rather than a public health office registering it as anything requiring action at all. There's also the matter of gamma-ray bursts, the single most energetic phenomenon the universe produces, capable of doing real, terrifying damage to a world unlucky enough to be caught directly in their path, even from far greater distances than this. It's a legitimate question, and one serious astronomers take seriously for other stars. But a gamma-ray burst isn't something every dying star produces. It requires a particular, relatively rare set of circumstances, extremely rapid rotation and, crucially, a very specific alignment, with the resulting beam of radiation firing out along the star's rotational axis, like a lighthouse, in a tight, narrow beam, rather than in every direction at once. Betelgeuse shows no sign of spinning anywhere near fast enough to produce one, and even if it somehow did, its rotational axis isn't aimed anywhere close to Earth's direction. The lighthouse, if it exists at all, isn't pointed this way. This is, as far as anyone can responsibly determine, simply not one of the ways this particular story could have ended badly for us. It's worth pausing on why that reassurance rarely travels as far as the fear does. A calm, hedged, properly qualified explanation of orbital mechanics and rotational axes is not, by any reasonable measure, a thrilling piece of content. It doesn't have a thumbnail. Fear is simple, immediate, and easy to share with a single tap. Safety requires several paragraphs and a working knowledge of what a light year actually is. The garage broadcast wins the algorithm every time, not because it's more convincing, but because it's less effort to believe. So, dazzling, yes. Genuinely unprecedented in recorded human history, yes. Dangerous in any meaningful sense to anyone standing on this planet looking up at it? No, which leaves the far gentler, stranger questions about what actually changes here on Earth while all of this is happening, and those turn out to be worth just as much of our attention as the ones about danger. Nocturnal wildlife, for instance, is going to have an extremely confusing few weeks. Countless species, migratory birds navigating by starlight, sea turtles finding their way to the ocean by the relative brightness of the horizon, insects that orient themselves by the moon, rely on the night sky staying broadly, reliably dark and predictable in ways it has been for the entire span of their evolutionary history. A single point of light, bright enough to rival the moon, sitting in a completely different part of the sky, in completely the wrong season, is exactly the kind of disruption that has, in far smaller forms, already been shown to send migratory animals off course. Ornithologists and conservation biologists are going to have an unusually busy season, and more than a few research papers are eventually going to open with some version of the sentence, "In the months following the appearance of an unusually bright new light source in the northern winter sky." For the rest of us, the effect is likely to be less scientific and considerably more collectively strange. Observatories that spent decades studying quiet, cooperative patches of empty sky are about to become the most oversubscribed real estate in the scientific world. Every available instrument reoriented toward one small patch of Orion for months at a stretch. Cities are going to notice their light pollution problem in reverse, briefly. As a single star competes with streetlights for attention, campsites near dark sky parks are going to fill up months in advance with people who have never previously shown any particular interest in astronomy. hoping to see with their own eyes something that last happened at a comparable distance before anyone alive had ever been born, and that nobody alive is likely to see again. Parents are going to wake their children up in the middle of the night specifically to look at it, the way parents have always woken children up for meteor showers and eclipses and the rare, genuine spectacles the sky occasionally offers for free. And somewhere, almost certainly, someone is going to propose a toast to a star that, as far as it's concerned, finished doing all of this a very long time ago and never got to see a single second of the reaction. There's a particular kind of quiet that tends to fall over a crowd gathered to watch something like this, once the initial excitement wears off and people simply stand there looking up. It isn't the quiet of fear. It's closer to the quiet of a total solar eclipse, or a very good meteor shower, or any of the handful of moments the sky occasionally offers that make a crowd of strangers stop talking at the same time, for the same reason, without anyone having to ask them to. Whatever else this event turns out to mean for astronomy, for wildlife, for the slightly overwhelmed observatory staff fielding calls at 3 a.m, it will also, for one stretch of weeks, have simply been beautiful, bright enough to cast a shadow, gentle enough to do no harm, and old enough that whatever's actually happening to the star responsible finished happening long before any of us were born to see it. At an observatory in Hawaii, a system that was supposed to spend that particular week studying the atmosphere of a distant, unremarkable exoplanet gets a terse override message from Mission Control at 2 a.m. local time, cancelling 4 months of carefully negotiated telescope time in a single sentence. Nobody objects. The astronomer whose exoplanet just lost its slot is, by her own later admission, one of the first people in the building to start celebrating, because she understands immediately what everyone in the field is about to understand within the hour. The queue for telescope time doesn't matter anymore. There's only one target left worth pointing anything at, and every Sirius instrument on and above the planet is about to be aimed at exactly the same 640-year-old patch of sky. What follows over the next several hours is very possibly the largest single act of scientific cooperation in the history of the field, not because anyone organised it, but because nobody needed to. Word moves through the global astronomical community the way word moves through any close-knit profession when something enormous happens, fast, informally, and with an urgency that cuts straight through the usual bureaucracy of shared telescope time and competing research priorities. Within hours, requests that would ordinarily take committees months to approve are being waved through by directors working from home in their pyjamas, because everyone understands, instantly and without needing to be told twice, that whatever squabbles existed yesterday over whose project gets priority this month have just become almost comically unimportant. The neutrino detectors, as we've already met, had their moment first, hours before anyone with a telescope had anything to look at. Vast underground tanks of ultra-pure water and other exotic materials, built and buried specifically to catch the occasional, vanishingly rare interaction between a neutrino and ordinary matter, suddenly registering dozens of interactions within a span of seconds, where they might ordinarily expect one every few days. It's worth pausing on how strange that detection actually is. As a piece of scientific infrastructure, enormous facilities, built at enormous cost, designed for years to wait patiently for an event that might never come in the lifetime of anyone who built them, exist for precisely one reason. So that, on the one occasion it actually happens, humanity gets a few hours' notice that something has gone catastrophically, spectacularly wrong with a star before a single photon confirms it. Tonight, for the first time in the era of modern neutrino astronomy, that patient bet finally pays out, and it pays out spectacularly. Then there's a possibility rarer still, one that even seasoned astronomers are reluctant to promise out loud until the data actually confirms it. Gravitational waves, ripples in space itself, predicted by Einstein over a century ago and only directly detected for the first time in 2015, are typically the signature of genuinely extreme cosmic collisions. Black holes merging, neutron stars colliding, events involving objects so dense and so violent that they physically stretch and squeeze the fabric of space measurably, even across vast distances. A star's core collapse can, in principle, produce a much fainter gravitational wave signal of its own, one that's normally far too faint and far too distant to catch with existing instruments. But normally too faint assumes a normal distance, and there has never before been a core collapse this close, while humanity happened to have gravitational wave detectors switched on and listening. If the signal is there at all, and nobody will know for certain until the data has been combed through by teams working in shifts around the clock, it will be the first time anyone has ever directly measured the actual shape of space itself, flexing in response to a single star's death, rather than two extraordinarily massive objects colliding with each other. Space telescopes, meanwhile, are chasing something that ground-based observatories, however good, simply cannot see at all. The earliest flash of ultraviolet and X-ray light escaping the star in the first moments the shockwave finally breaks through its surface, a brief, brilliant spike of high-energy radiation that gets almost entirely absorbed by Earth's atmosphere before it ever reaches ground level. For decades, catching this exact moment, called shock breakout, the instant an exploding star's surface first registers that the end has arrived, has existed mostly as a target of hopeful theoretical modelling, glimpsed only rarely by accident in far more distant galaxies, in data collected for entirely different purposes. Tonight, for once, there's advance warning. The neutrino burst arrived hours before the light, which means that for the first time in the history of the field, telescopes above the atmosphere know almost exactly when and where to look before the flash even happens, rather than stumbling across the evidence afterward in archived data and wishing they'd been paying closer attention at the time. Radio telescopes join in on their own delay, weeks and months down the line, once the expanding debris has thinned enough for radio waves generated deep within the wreckage to finally escape and travel freely. X-ray observatories keep watching for years afterward, tracking the shockwave as it continues ploughing outward through whatever gas and dust the star spent its final centuries shedding into the space around it, the same slow exhalations from earlier tonight, now being lit up from behind like a curtain suddenly backlit by a spotlight nobody had switched on in 640 years. Every wavelength tells a slightly different part of the story, on a slightly different schedule, and the full picture won't really be complete for years, possibly decades, as observatory after observatory keeps checking back in on the same small patch of Orion, the way you'd keep checking in on news that mattered too much to only read once. It's worth sitting for a moment with what all of this adds up to, because it's easy to let the individual details, neutrinos here, gravitational waves there, an ultraviolet flash somewhere else, slide past without noticing the shape they make together. This is what astronomers call multi-messenger astronomy, the same single event observed simultaneously through entirely different kinds of signals, arriving by entirely different physical means, on entirely different schedules, each one telling part of a story the others can't. The neutrinos carry news from the very core, seconds after collapse. The gravitational waves, if they're there, carry news of the geometry of that same collapse, encoded in the shape of space itself. The light, first the ultraviolet flash, then the long, slow, visual spectacle stretching across months, carries news from progressively further out, each wavelength arriving on its own delay, each one a different messenger from a different depth of the same single event. Ask, again, when exactly this happened, and the honest answer keeps multiplying rather than narrowing. The neutrinos say one thing, the light says another, and every instrument on Earth is, in its own way, correct. There's a kind of scientific humility built into all of this that's easy to miss under the sheer noise of the event. Every one of these instruments, the underground neutrino tanks, the gravitational wave detectors sensitive enough to notice a change in distance smaller than the width of a proton, the space telescopes, the radio dishes, was designed and built by people who had no guarantee any of it would ever detect the thing it was built for. Entire careers have been spent maintaining instruments tuned for an event some of their builders privately doubted they'd live to see. Tonight, every one of those quiet, patient bets comes due simultaneously, and the sheer relief radiating out of observatory break rooms across a dozen time zones is, by several accounts, almost as remarkable as the data itself. Back on the ground, away from the observatories and the reoriented satellites and the astronomers arguing cheerfully over shared data in a dozen languages at once, a family in a backyard several time zones away from all of it has pulled some old lawn chairs out of a shed that hasn't been opened since the previous summer, wrapped themselves in blankets against a chill nobody's bothered to go back inside for, and settled in to watch, together, a portion of the sky none of them have ever paid this much attention to before in their lives. Nobody in this particular yard understands what a neutrino is, or could explain the difference between a gravitational wave and an ordinary one, and none of that matters even slightly to what's actually happening here. They know, the way people simply know about certain nights without needing a scientific justification for it, that this is one they'll still be describing to people decades from now. Where they were, who they were with, how cold the grass felt through the blanket, how quiet everyone got once they actually found it. Every single telescope on and above the planet is pointed at the same 640-year-old light. So, for one unremarkable evening, in an unremarkable backyard, is a family who came outside for no better reason than that everyone else seemed to be doing it too, and it seemed, on a night like this, like exactly the right way to spend a few hours together. 5 years later, give or take, a graduate student at a conference stands up during the question period after a keynote and asks something that gets a small, knowing laugh from half the room before the speaker even answers. Is it a neutron star or a black hole yet? The speaker, who has clearly fielded this exact question more times than she can comfortably count, gives the honest answer, which is the same answer it's been for years, and will likely remain the answer for a good while yet. Ask me again in 10 years. It's worth explaining why that question, which sounds like it should have a tidy, satisfying answer by now, turns out to be one of the stubbornest open cases in the whole field, and why the not knowing is, in its own way, just as interesting as either answer would have been. But first, the part of the story that does resolve visibly on a timescale, human beings can actually watch unfold. In the weeks immediately following the explosion, the fading of Betelgeuse's brightness isn't simply a matter of the initial flash dying down. A meaningful portion of that lingering glow, stretched out across the following months, comes from something almost bureaucratic in its precision: a large quantity of radioactive nickel, freshly forged in the extreme conditions of the explosion itself, decaying steadily into cobalt and then into stable iron, releasing energy the entire way down on a schedule as fixed and predictable as a clock. Astronomers can measure this decay curve and use it to weigh with a real precision exactly how much radioactive material the explosion actually produced, a strange, pleasing bit of bookkeeping in which a star's death months later hands back an itemized receipt for exactly what was created in the process of ending it. Beyond that glow, the material itself, everything blasted outward by the original shockwave, moving at a meaningful fraction of the speed of light, keeps expanding, steadily, relentlessly, outward into the surrounding darkness. This is where the story's next several centuries actually take place, and it's worth remembering for scale what a supernova remnant of this kind eventually becomes. The Crab Nebula, born from that 1054 explosion witnessed independently by observers on opposite sides of the planet, has spent the better part of 1,000 years quietly expanding, and today stretches across a distance of roughly 11 light-years, an object so large that light itself, the fastest thing there is, would need over a decade to cross from one edge to the other. Betelgeuse's own remnant is going to do something similar, just getting started on a journey that will still be unfolding long after every person reading or listening to this sentence has been dead for centuries in turn, expanding and thinning and eventually merging so thoroughly with the surrounding interstellar material that within a few 100,000 years, calling it a distinct object at all will stop making much sense. Watch it across the decades if you had the patience of an institution rather than a person, and the shape of the thing keeps changing character. In the first few years, it's essentially a fireball, hot, glowing, chaotic, still cooling from the sheer violence of its own creation. Within a century or two, it starts to resemble something closer to lattice work, delicate glowing filaments threading through darker gaps, the same structure you can see today in photographs of the Crab Nebula and its slightly younger cousins scattered across the galaxy, each filament a place where the outward rushing debris happened to compress or cool just slightly differently than its neighbours. By the time it's a few thousand years old, it starts colliding properly with the thin gas already drifting through interstellar space, sweeping it up the way a snowplow gathers snow, slowing gradually, glowing for a while from the sheer friction of the collision, before finally, over tens of thousands of years, thinning out and merging so completely with its surroundings that no future astronomer, looking at that patch of sky, would ever guess a single star used to sit there at all. That's the outer story, the fireworks, the debris, the glowing shell slowly dissolving into the wider galaxy. The inner story, the one the graduate student was actually asking about, concerns something far smaller and far stranger. Whatever's left behind at the very centre, where the core itself collapsed in that first fraction of a second, long before any of the visible drama had even started. Here's the shape of the uncertainty, and it's a genuinely satisfying kind of uncertainty, the sort that comes from a real physical threshold rather than simple ignorance. When a massive star's core collapses, what's left behind depends almost entirely on exactly how much mass survives the process. And exactly how much is doing a great deal of work in that sentence, because it turns out to sit uncomfortably close to a very specific, very unforgiving dividing line. If the collapsed remnant core ends up below roughly 2 to 3 times the mass of the Sun, the collapse halts at an extraordinary but stable configuration. A neutron star, a leftover core no wider than a modest city, so dense that a single teaspoon of its material would weigh on Earth roughly as much as an entire mountain. Neutron stars are strange and wonderful objects in their own right. Some of them spin hundreds of times a second, sweeping beams of radiation across space like a cosmic lighthouse, detectable from Earth as some of the most precise natural clocks in the entire universe. But if the remnant core ends up just slightly heavier than that threshold, and for a star Betelgeuse's size, feeding on the fallback of material still raining down from the explosion in the hours immediately following collapse, that threshold sits agonizingly close to the estimated range. Even a neutron star's extraordinary resistance isn't enough. Gravity wins a second time, more completely than the first, and what's left instead is a black hole, a region of space where the collapse never actually stops at all, compressing down toward a mathematical point that no known physics can currently describe with any real confidence. The honest, frustrating, genuinely fascinating truth is that Betelgeuse's exact starting mass, and exactly how much of that mass it shed over its final centuries through its restless, star-sized exhaling, and exactly how much fallback material rains back down onto the newly formed core in the hours after collapse, all sit close enough to that dividing line that confident astronomers, working from the same data, land on different sides of the answer. Some models favour a neutron star, likely one spinning fast enough to eventually announce itself as a pulsar, a clean and detectable radio signal confirming its presence for anyone patient enough to keep listening. Other models favour a black hole, in which case there may be no clean confirming signal at all. Simply an absence, a hole in the data where a star's remnant core should be, detectable only through its gravitational influence on the material still swirling and falling into it. Which is why the graduate student's question doesn't really have an answer yet, and might not for years, possibly decades, as radio telescopes keep patient watch over that one small patch of sky, waiting for the distinctive rhythmic pulse of a spinning neutron star to show up, or waiting, just as attentively, for its continued and total absence to become itself a kind of answer. It's the sort of open question that used to bother beginning students far more than it bothers the people who've spent their careers with it. Some of the most interesting places in the universe, it turns out, are the ones sitting exactly on top of the line between two very different outcomes, close enough that nobody gets to know in advance which side they'll land on, and patient enough, as a field, to simply wait and watch for as long as it takes to find out. There's something quietly fitting about ending up here, of all places, with a question this open. A star that spent 10 million years living fast, that shed its warning signs in a language nobody could read correctly the first time, that announced its own death in 3 different signals arriving on 3 wildly different schedules, doesn't owe anyone a tidy conclusion just because the fireworks are over. It's still, all these years later, keeping something back, not out of any intention. Stars don't have intentions, but simply because the physics genuinely hasn't decided yet which way it's going to fall, and no amount of human impatience is going to make it decide any faster. The graduate student will ask again in 10 years. So will the person who trains under her. Eventually someone will get an answer. For now, the not knowing is, itself, exactly the point. Step outside if you'd like to, right now, tonight, wherever you happen to be listening to this. Find a patch of sky away from the worst of the streetlights. Give your eyes a minute or two to adjust the way they always need to, and look for the hunter. The belt first, 3 stars in a neat, unmistakable line, and then up and to the left, to the shoulder. It's there, exactly where it's always been. Burning that same soft, patient orange-red It's burned for as long as anyone alive has been looking up at it, utterly unchanged, utterly undramatic, doing absolutely nothing tonight, except quietly existing the way it has for the entire span of recorded human history. Nothing has happened yet. We should sit with that for a moment, because it deserves more than a passing mention. Everything we've spent the last 2 hours living through together, the astronomer woken at 3:47 in the morning, the neutrino detectors lighting up on 3 continents at once, the phone that wouldn't stop ringing, the family in the backyard with the blankets and the borrowed lawn chairs, the graduate students still waiting for an answer about a neutron star or a black hole. None of it has happened. Not yet. Possibly not for tens of thousands of years yet. Betelgeuse, as far as anyone standing under tonight's actual sky can tell you, is exactly as intact, as patient, as quietly unexploded as it was the night before any of us started this particular story. This wasn't a trick, and it wasn't a documentary, whatever it may have felt like along the way. It was something closer to a very long, very careful thought experiment, built entirely out of real physics, real numbers, real events, Betelgeuse's actual mass, its actual distance, the actual dimming it went through in 2019, the actual discovery of its actual companion star in 2025, arranged into a story about a night that hasn't come yet, told as though it already had. Because that turned out to be the only honest way to make 640 years of waiting feel like something a person could sit with for a couple of hours before falling asleep. It's worth being honest, too, about why it was worth doing this way at all, rather than simply listing the facts and letting them sit there on their own. Told as a list, most of tonight's material is a set of impressive but slightly abstract statistics, a star's mass, a distance in light years, a probability range for 2 possible remnants. Lived through, even as an imagined night, the same facts become something closer to what they actually are, an ending that is, in every sense that matters, still arriving, still travelling, still unresolved, no matter how completely we allow ourselves to imagine its arrival for a couple of hours in the dark. Here's what is true, and worth being completely honest about now that we've come this far. Betelgeuse absolutely will explode one day. Every single thing said tonight about why, the iron core, the sudden absence of anything left to push back against gravity, the neutrino burst, the shock wave, the years afterwards spent waiting to find out what's left behind. Every bit of that is going to happen, exactly as described at some point. What nobody can tell you, what nobody currently alive will ever be able to tell you with any real confidence, is when. The honest range astronomers give runs from possibly quite soon on a cosmic time scale to possibly not for another 100,000 years, which is such an enormous span of uncertainty that it's barely worth calling a prediction at all. It might happen tonight, an hour after you finish listening to this. It might not happen until long after every language currently spoken on this planet has changed beyond recognition. Nobody gets to know in advance. That's simply the deal with a star this far along and this quietly unpredictable. And here's the part that makes the not-knowing stranger still and brings us back properly to something that's been sitting quietly underneath tonight's entire story, waiting for exactly this moment. Because of the distance involved, that same 640 light-years we spent so long with earlier tonight, there is in fact no way to rule out that it already has happened, not in our story, in actual, real, ongoing history. If Betelgeuse's core collapsed at some point during your own lifetime, last week, 5 years ago, the year you were born, nobody on Earth would have the faintest idea yet. the light wouldn't arrive for centuries. Somewhere out there, right now, tonight, the news may already be travelling toward us, already decided, already unstoppable, and we are, every single one of us, simply going about our lives in the calm, ordinary interval before a letter that's already been sent finally gets delivered. Which brings us back at last to the question we've been quietly circling since the very first chapter tonight. When does an event actually happen? We asked it first about light travel time, and then again about the neutrino burst arriving hours before the light, and again about the shock wave taking its own sweet time crossing the star's own bulk, and again about the gap between a detector registering something and a headline finally explaining it to someone eating breakfast. Lay all of those moments out together now and look at how many candidates there really are for the single word when. There's the instant the core collapses, quieter and faster than anything else in this entire story, over before you could possibly notice it starting. There's the moment, hours later, the neutrinos slip free of the star entirely, already carrying the news outward at the speed of light, while the star's own surface still looks completely untouched. There's the moment, later still, the shock wave finally breaks through that surface, and the light itself begins its own 640-year journey. There's the moment, centuries after that, the light actually reaches a small blue planet that has spent its entire existence quietly orbiting a completely different, much closer star. There's the moment a detector somewhere registers it, the moment an astronomer's phone starts ringing, the moment a headline gets written, the moment a family drags some old chairs out into a backyard, the moment a child, entirely by accident, happens to be looking in exactly the right direction at exactly the right second. None of those moments is wrong. None of them, on its own, is quite complete either. An event this large doesn't have a single when the way a hand clap does. It has a whole procession of whens, arriving in careful order, each one true for someone, none of them true for everyone, stretched out across a gap of time so enormous that the beginning and the end of the story might belong to entirely different eras of human history, and never once overlap. It's a little like asking when a letter was actually written once you've received it. Is it the moment the pen touched the paper, the moment it was sealed, the moment it left the sender's hand, or the moment, weeks or years later, it finally lands on a doormat and gets read for the first time, long after the person who wrote it has moved on to an entirely different life, possibly without remembering the letter was ever sent at all. Every one of those moments has a fair claim to being when it happened. None of them fully settles the question, because the question was never really built. For events this stretched out in time, we just don't normally notice, because most of the letters in our lives arrive within days, not centuries. Maybe that's the more honest way to think about endings generally, star-sized or otherwise, not as a single clean instant everyone agrees on, but as something that keeps arriving, in stages for different people at different times, long after the part that actually mattered has already quietly finished happening somewhere far away, without an audience, without ceremony, without anyone at the time even knowing to look. For now, though, and this part is real, not a thought experiment, not a story constructed for the sake of an evening, Betelgeuse is still there, whole, unexploded, sitting exactly where it's supposed to be sitting, burning exactly the way it's always burned, offering absolutely no indication tonight of when its letter is finally going to arrive. Which means there's still time, at least for tonight, to go back outside, find that same patch of sky one more time, and simply look at it the way people have always looked at it. Not as a countdown, not as a mystery waiting to be solved, but as a star. Just a star for now, doing what stars do, patiently on a schedule that belongs entirely to itself. Here's a small, quiet fact about Orion that has nothing to do with Betelgeuse exploding, and everything to do with what Orion actually is, underneath the shape we've all agreed to see in it. It isn't a group of stars, not in the way that phrase suggests. It's a coincidence, a genuinely enormous coincidence of perspective. Stars sitting at wildly different distances from Earth, some of them not even remotely near each other in space, that simply happen to line up from this one particular vantage point in this one particular corner of the galaxy into a shape that looks, to a species prone to seeing shapes in almost anything, like a hunter with a belt and a raised arm. Betelgeuse sits roughly 640 light-years away. Rigel, the bright blue-white star marking the opposite foot, sits at something closer to 900 light-years. Further still, and shining with an entirely different kind of light, a hotter, younger, faster-burning star that has nothing in common with Betelgeuse, except that both happen to fall by chance within the same small patch of sky as seen from here. Some of the stars forming the belt sit further away still, over 1,000 light-years out, genuinely distant neighbours of Betelgeuse and Rigel alike, sharing nothing but a lucky alignment. If you could somehow fly out and view this same cluster of stars from a wildly different angle, from somewhere on the far side of the galaxy, say, the hunter would simply vanish. There'd be no belt, no shoulder, no raised arm, just scattered stars, at their true and wildly different distances, with no relationship to one another beyond the ordinary fact of existing in the same rough neighbourhood of a very large galaxy. Which means that everything we've spent tonight calling Orion was never really one thing at all. It's a trick of standing in exactly the right place, at exactly the right moment in cosmic history, to see an accident of geometry and mistake it for a picture. Every culture that ever looked up and found a hunter, or a canoe, or three sisters, or a plough, depending on which tradition you happened to be born into, was doing the same thing. Finding a story in stars that have absolutely no relationship to each other beyond a shared trick of the light and a shared willingness on our part to connect dots that were never actually asking to be connected. And it doesn't even hold still. This is the part that tends to surprise people the most, more than the different distances, more than the coincidence of the alignment itself. The stars of Orion are moving, all of them, all the time, drifting through space at their own individual speeds and in their own individual directions. And the only reason the hunter still looks like a hunter tonight is that, on a human timescale, that drift is achingly slow. 50,000 years ago, before anyone had invented writing, before agriculture, before most of what we'd recognize as civilization, Orion looked noticeably different in Earth's sky. The belt bent at a slightly different angle, the proportions subtly off from the shape we know. 50,000 years from now, it'll have drifted again, slowly reshaping itself into some other pattern entirely, one that whatever descendants are still around to look up will name after whatever stories happen to matter to them by then. The hunter we've spent tonight discussing was never permanent. It was only ever passing through this particular shape, for this particular stretch of time, the same way a cloud passes through the shape of a rabbit or a ship for the brief minute you happen to be looking at it before the wind moves it into something else. There's a strange comfort tucked inside that fact if you let it sit for a moment. Every civilization that has ever looked up and found this same hunter, the ones who first named it, the ones who sailed by it, the ones who simply pointed it out to a child after dinner without knowing anything about its physics at all, was, in the broadest possible sense, sharing a view with every other civilization that came before and after, a continuity stretching back further than any single culture, any single language, any single idea about what the shape even meant. Orion doesn't belong to anyone in particular. It's simply been on loan to whoever happened to be alive and looking up, for a temporary stretch of cosmic time that has, by pure chance, included the entire span of human history so far. Betelgeuse's eventual explosion, whenever it finally comes, will simply be a faster, more dramatic version of a change that was always quietly underway regardless. The slow drift would have altered Orion eventually with or without a supernova. The explosion just does the job all at once, in a single unmistakable evening, rather than over the patient tens of thousands of years the drift alone would have taken. One shoulder suddenly and permanently gone, and every star chart, every planetarium show, every parent tracing the shape out for a child after dinner, having to quietly adjust to a hunter with a different outline than the one that stood in that spot for the entire span of recorded human history. It's worth sitting for just a moment with how strange that actually is, a shape that has meant roughly the same thing to an almost unbroken chain of human cultures across thousands of years and half the inhabited world, from ancient Babylon to medieval Arabia, to a child in a backyard earlier tonight, is going to change permanently the very first time any of those cultures happens to be watching. Every person who's ever traced this constellation with a finger, in every language that's ever had a word for it, has been describing a shape with a quiet, built-in expiration date, without a single one of them knowing it. We only happen to be the generation, whenever that generation eventually turns out to be, unlucky or lucky enough, depending entirely on your taste for cosmic drama, to actually be looking up on the specific night it finally changes. But that generation isn't tonight's generation, or at least there's no way yet to know that it is. Which brings us back to where we started this whole evening, in the most literal sense available. Somewhere, out there, right now, someone is standing in a backyard or on a balcony, or pausing halfway across a parking lot on their way somewhere else entirely, and glancing up, out of habit, at a sky they've looked at 1,000 times before without a second thought. They find Orion easily, the way people always seem to, once they've been shown it even once. Belt first, then up to the shoulder, and there it is, Betelgeuse, burning that same patient, undramatic orange-red. It's burned for the entirety of this person's life, for the entirety of their parents' lives, for the entirety of every life anyone currently walking this planet has ever lived. They see nothing unusual at all. No flare, no sudden brightening, no 640-year-old letter arriving with news that's going to rearrange one of humanity's oldest and most recognizable shapes forever. Just a star, doing what it's always done, on a schedule that belongs entirely to itself and to nobody watching it from here. They glance away after a few seconds, the way people do, already thinking about dinner, or the drive home, or the 100 small ordinary things a single evening is actually made of, without the faintest idea that they've just spent a moment looking at one of the most quietly uncertain objects in the entire visible sky. A star that will, eventually, undoubtedly without any possible exception, do exactly what we've spent this whole evening imagining, just not as far as anyone can tell tonight. And that, in the end, might be the most honest place this story could possibly leave us. Not with an ending, because there isn't one to give yet, but with an ordinary person on an ordinary night, looking up at an extraordinary star and seeing, for now, absolutely nothing extraordinary at all, which is, in its own quiet way, exactly as it should be. The story isn't over. It hasn't even properly begun. It's simply waiting, patiently, the way it always has, for a letter that's already been written, sealed and sent, somewhere out there in the dark, and that, for reasons entirely its own, hasn't quite decided yet when it's going to arrive. Wherever you are right now, however dark the room has gotten, there's a strange kind of comfort in knowing that above the ceiling, above the clouds, past the point where anyone could reach it, that same patient orange light is still making its way toward us. Not tonight, probably. Maybe not for longer than any of us will be around to notice. But somewhere out there, in the dark between here and Orion, an answer is already travelling. It left a long time ago, or it hasn't left yet, and there's no way from down here to know which. That's not really a reason to stay awake wondering. If anything, it's the opposite. A letter that's been in transit for 600 years isn't going to arrive any sooner for anyone's watching. The star will keep doing what it's always done, on a schedule that was never any of our business to begin with, and the rest of us get to do what we've always done in the meantime. Go to sleep, wake up, glance at the sky out of habit more often than curiosity, and let the waiting take care of itself. There's something almost restful about a mystery this size, once you stop trying to solve it tonight. Most of the things that keep us up worrying have some kind of deadline attached, some date by which we'll finally know. This one doesn't and won't, not for as long as anyone reading or listening to this is likely to be around. It's the rare kind of not knowing that asks nothing of you. You don't have to prepare for it. You don't have to watch for it. You just get to carry it around quietly, the way you'd carry a good, unfinished story, content to let it stay unfinished a while longer. So let the shoulder of the hunter keep its quiet secret a little longer. Let it hang there, unremarkable, exactly where it's supposed to be, for one more ordinary night among however many it has left. Whatever answer is already on its way will get here when it gets here, and there will be people to receive it, the same as there always have been. For now, there's nothing left to do but close your eyes and let it wait. Good night and sleep well. The Sleepy Astronomer.